Hello, everyone. Welcome to our Deep Dive podcast, where today we'll be reviewing the DINOv3 paper from Meta AI Research. Are you ready to explore the latest in self-supervised learning for computer vision?
Absolutely. DINOv3 has been making waves in the vision community. It promises to push the boundaries of self-supervised learning, eliminating the need for manual data annotation. Shall we start with the big picture?
Yes, let's begin with the motivation. The authors highlight that self-supervised learning, or SSL, can scale to massive datasets and larger architectures, without being tied to specific tasks or domains. This means a single algorithm can learn from diverse sources, like natural and aerial images.
That's a huge advantage. Unlike supervised or weakly supervised methods, which need labeled data or metadata, SSL can leverage raw, unlabeled images. This opens up training on virtually unlimited data, which is especially useful for large-scale visual encoders.
The DINOv3 paper builds on the success of DINOv2, which already showed impressive results in image understanding and pre-training for complex domains, such as histopathology and medical imaging.
And the key properties of SSL models are robustness to input distribution shifts, strong global and local features, and rich embeddings for scene understanding. Since SSL models aren't trained for specific downstream tasks, they produce versatile and robust features.
That's right. For example, DINOv2 models perform well across diverse tasks and domains without task-specific fine-tuning. A single frozen backbone can serve multiple purposes, which is a big deal for practical applications.
But scaling SSL isn't without challenges. The paper mentions issues like collecting useful data from unlabeled collections, knowing the optimization horizon, and the degradation of feature quality during long training runs, especially with large models.
Yes, and that's where DINOv3 comes in. The authors address these challenges by careful data preparation, model design, and optimization. They also introduce a new method called gram anchoring to tackle the degradation of dense feature maps.
Gram anchoring sounds intriguing. But before we get into that, can we talk about the evolution of SSL methods? The paper provides a historical perspective, showing how SSL has quickly caught up with supervised and weakly supervised methods in terms of ImageNet accuracy.
Indeed, SSL started later, but has now reached the ImageNet accuracy plateau of recent years. More importantly, SSL offers high-quality dense features, which are crucial for tasks like segmentation and depth estimation.
DINOv3 significantly improves over weakly supervised models on dense tasks. The paper shows that DINOv3 outperforms the best-in-class weakly supervised models on benchmarks like semantic segmentation and 3D keypoint matching.
That's a major achievement. The versatility of DINOv3 is enabled by scaling both the model size and the training data. The authors trained a DINO model with 7 billion parameters and then distilled its knowledge into smaller, more efficient variants.
Distillation is a clever way to make large models practical. The DINOv3 family includes Vision Transformer ViSH-AT, small base and large, as well as convex-based architectures. The ViT large model, for example, achieves performance close to the original 7B teacher.
Let's talk about the core contributions of the paper. First, they use advanced data curation techniques to build a massive and diverse training dataset. Second, they scale up the model architecture to 7B parameters with custom modifications.
Third, they introduce gram anchoring, which regularizes the training to maintain high-quality dense features even during long training schedules. And finally, they apply post-hoc strategies like high-resolution adaptation and efficient distillation.
The data preparation process is fascinating. They start with a pool of 17 billion web images from Instagram, then use hierarchical k-means clustering and retrieval-based curation to create a balanced and relevant dataset.
They also mix in raw datasets like ImageNet 1K, ImageNet 22K, and mapillary street-level sequences. During training, they use a sampler to mix different data parts, sometimes using homogeneous batches from ImageNet 1K and sometimes heterogeneous batches from all components.
Their ablation study shows that no single curation technique works best across all benchmarks, but their full pipeline achieves the best overall performance. This highlights the importance of data diversity and balance.
On the model side, they scale up to 7B parameters using a custom VIT architecture with modern position embeddings and regularization techniques. They also switch from cosine schedules to constant hyperparameter schedules, which simplifies optimization.
That's a smart move. It allows them to continue training as long as downstream performance improves and reduces the number of hyperparameters to tune. They use DINOv3 optimizer, a large batch size, and a multi-crop strategy for data augmentation.
Now let's dive into gram anchoring. During extended training, they observed that while global metrics improve, performance on dense tasks like segmentation declines. This is due to the loss of patch-level consistency in the feature maps.
To address this, they introduce a gram matrix-based loss. The idea is to regularize the pairwise similarities between patch features, pushing the student's gram matrix towards that of an earlier, well-performing teacher model.
This approach preserves the structure of similarities without constraining the features themselves. They apply the gram loss only on global crops and started after 1 million training iterations, which is efficient and effective.
The results are impressive. Incorporating gram anchoring leads to immediate improvements on dense tasks, with significant gains on benchmarks like ADE20K. They also leverage higher resolution features for the gram teacher, further enhancing patch-level consistency.
The qualitative visualizations in the paper show that DINOv3 produces much cleaner and more coherent feature maps compared to previous models. This translates into better performance on tasks like segmentation, depth estimation, and object discovery.
Speaking of tasks, the paper evaluates DINOv3 on a wide range of benchmarks. For semantic segmentation, DINOv3 outperforms both self-supervised and weakly supervised baselines by large margins.
On monocular depth estimation, DINOv3 achieves the lowest root mean squared error, surpassing even models distilled from heavily supervised segmentation models like SAM.
For 3D correspondence estimation, DINOv3 leads in both geometric and semantic keypoint matching, highlighting its strong 3D awareness. It also excels in unsupervised object discovery, video segmentation tracking, and video classification.
The global features of DINOv3 are also robust. On ImageNet and its variants, DINOv3 matches or exceeds the performance of the best weakly supervised and supervised models, especially on out-of-distribution and fine-grained classification tasks.
In instance recognition, DINOv3 achieves the highest mean average precision on landmark, art, and historical image retrieval datasets. This shows its versatility across both global and dense tasks.
The paper also demonstrates DINOv3 as a foundation for complex computer vision systems. With a frozen backbone, they train lightweight decoders for object detection, semantic segmentation, and monocular depth estimation, achieving state-of-the-art results.
For object detection, their plain DTAR model with a frozen DINOv3 backbone reaches state-of-the-art performance on COCO and COCO-O, outperforming models with much larger trainable parameter counts.
In semantic segmentation, their mask-to-former-based decoder with a frozen DINOv3 backbone matches or exceeds the best published results on ADE20K, COCO-Stuff, and VOC 2012.
For monocular depth estimation, combining DINOv3 with Depth Anything v2 yields new state-of-the-art results on multiple real-world datasets, all with a frozen backbone.
They also swap DINOv2 for DINOv3 in the visual geometry grounded transformer pipeline, achieving state-of-the-art results on 3D geometry tasks like camera pose estimation and multi-view depth estimation.
The DINOv3 family of models is thoroughly evaluated. The distilled VNIT and ConvNext variants cover a wide range of computational budgets, making them suitable for various deployment scenarios.
The VIT-H Plus model, for example, achieves performance close to the 7B teacher, validating the effectiveness of their distillation process. The ConvNext models, distilled from the 7B teacher, outperform supervised convex models on dense tasks, and scale better with input resolution.
They also train a text encoder aligned with DINOv3, enabling zero-shot inference and open vocabulary segmentation. The text-aligned DINOv3 model achieves excellent dense alignment performance while staying competitive in global alignment tasks.
The universality of DINOv3 is showcased by training a 7B model on satellite images. The DINOv3 satellite model sets new state-of-the-art results on canopy height estimation, semantic segmentation, and object detection in remote sensing benchmarks.
Interestingly, the DINOv3 web model, trained on diverse web images, also performs competitively on geospatial tasks, highlighting the generalization power of SSL.
The environmental impact of training such large models is addressed. The authors estimate the carbon footprint and compare it to other large-scale models, emphasizing the need for responsible AI development.
To sum up, DINOv3 represents a significant advancement in self-supervised learning for computer vision. By scaling data and model size, introducing gram anchoring, and applying efficient distillation, DINOv3 achieves state-of-the-art performance across a wide range of tasks without fine-tuning.
The DINOv3 suite of vision models offers a versatile and scalable solution for diverse applications, setting new benchmarks and demonstrating the promise of self-supervised learning in advancing computer vision.
That wraps up our review of the DINOv3 paper. We hope you enjoyed this deep dive into the latest in self-supervised vision models. Stay tuned for more paper reviews and discussions on cutting-edge AI research.
Thanks for listening, everyone. If you have questions or topics you'd like us to cover, let us know. Until next time, keep exploring the world of AI.